All right, this is the first recorded lecture here, which is actually section 5 or chapter 5 of the first part of the class. I will talk about the zoo or thermomagnetic effects. So I call this a zoo because these effects are all named effects, Nernst, Righi, Leduc, Etinghausen, Hall, whatnot. They all look the same, like penguins. You have to be able to identify them. So it may seem strange, but the person who feeds the penguins must identify each penguin individually, otherwise the fattest penguin will get all the fish. So let's revise a little bit what these tensors are. We saw Onsager, and we saw the flux of current and the flux of heat as a function of electric field or grad T, and these are non-canonical forms, but they are practical forms. With these conductivities, electrical conductivity tensor, this is the thermoelectric conductivity, I can call it. This is a thermal conductivity, it's part of the thermal conductivity. And this is then, well, related to LET by the reciprocity. Now, historically, of course, the named coefficients are the resistivity, which relates the electric field to the current, and the thermal power, which relates the electric field to the temperature gradient. Vice versa, the heat flux is related to the current flux by the Peltier coefficient and to the thermal conductivity, to the temperature gradient by the thermal conductivity. Now, in the reciprocities, if we were to transform this equation to its canonical form, we would have then anti-symmetry of the tensor. But since this is a non-canonical form, the reciprocity looks like this, and this is just a repeat of last lecture. Now, if we go to the historical thermoelectric system with Seebeck and Peltier coefficients, then we have seen how the resistivity tensor is the inverse of the conductivity tensor, and that's actually the inverse of LEE tensor. The Seebeck tensor, on the other hand, is LET over LEE. In tensorial form, it would actually be minus LEE to the power minus 1 dot LET. No, times. This is a matrix product. And the Peltier tensor would be conductivity tensor inverse times LTE. The Onsager relations then are that rho is an anti-symmetric tensor of the field, but this here is again the transpose. Same with thermal conductivity. In fact, the symmetries between electrical resistivity and thermal conductivity, electrical and thermal conductivities are exactly the same. And this then becomes a tensorial form of the Kelvin relation, which relates, in fact, these two to each other. The Peltier coefficient is the field times the transpose of the Seebeck coefficient, and if this is plus B, that's in minus B. So quite integrate. Thermal conductivity tensor here is related to the LTT. It has an LTT tensor element, but it has then here the heat that is carried by the Peltier effect due to the voltage that comes from the Seebeck effect. So that's why we have LTE and LET here and here. So let's go into a little bit more details in each of these LEEs and LTTs. So if I'm in a system where I have a magnetic field oriented along any arbitrary direction B, 1, 2, or 3, or XX, XY, XZ, then I have in the plane, XY plane of my sample, I have a conductivity, longitudinal conductivity tensor here. This is a Hall conductivity tensor. If we are in the XY plane, this is a Hall conductivity tensor if we are in the XZ plane. And so you end up with an XX, XY, and XZ component to each of the electrical conductivities themselves, with the transverse ones being the Hall ones. That green thingy is just this tensor here, and it's called the galvanomagnetic transport tensor. Everything else, so the thermal conductivity you recognize, we have the same symmetry as we have for the electrical conductivity. And then this is the Seebeckish, or the thermoelectric conductivity tensor, LET tensor, and this is the Peltier-ish, I don't know what to call that thing, Peltier conductivity tensor. You notice they again have the same symmetry, but all these are now the thermomagnetic transport tensors. Okay, what does that mean in practice? Well, first of all, anytime we measure a Nernst effect or a transverse thermoelectric effect or a magnetic field-dependent Seebeck effect, we need a notation, and the notation that we use in this class, and that's usually used in the field, is the first index is the flux or the field you apply. For example, if you measure resistivity, the first index is going to be the current density because you apply current and you measure voltage. The second index is the field value that you measure. So here, the second index in resistivity would be the electric field. The third index is the direction in which you apply the magnetic field. So we have rho 1, 2, 3 is E2 over J1 times B of B3. This is 1, 2, and 3 in arbitrary direction vis-a-vis your sample. Kappa is the same principle. The thermal powers are a little bit more delicate, of course. One is what you apply. Well, typically in a Seebeck coefficient measurement or Nernst or thermal power measurement, you apply a temperature gradient. So this is grad 1 T. Goes here. You measure an electric field, in this case it's a Nernst, in E2, and in this case you may apply a magnetic field B3. So a proper Seebeck would be alpha 1, 1 of no field. That is grad 1 and E1. Whereas this, if 1 and 2 were normal to each other, this would be a Nernst measurement. Okay. Now, that's the general case. There are the named effects. And now it's sort of interesting that all of them worked in this little town of Graz, except Seebeck and Peltier. Seebeck worked in Tallinn, in northern, that was back then in Prussia. Graz, of course, is in Austria. And Peltier was a Frenchman. He was a very wealthy watchmaker who retired at age 30, extremely wealthy. And then he did these fancy experiments that worked in thermoelectricity. I can't do that. So in Graz, we will find together Ettingshausen and Nernst, right next to Boltzmann, and other names that you probably know, like Arrhenius for the Arrhenius plots. This is the physics faculty in 1913. Much did they know that a year later, the whole thing would fall apart with World War I. Okay, so now that you know who these people are, let's go over their effects. Oh, I didn't mention Edwin Hall. Hall was here. Okay, so Hall effect. Here is my sample. We'll take it to be a parallel pipette, and we will take that, the electric flux lines and the field lines, well, the electric flux lines, let's say in the beginning, at zero field, are nice and parallel to the sides. So you apply current to the thing in this direction, which creates a current density in Jx. You have Ex is the longitudinal electric field. That gives you the resistivity, of course. Now the Hall effect, you're going to apply B in this direction, Bz, and that means you're going to develop an electric field in the y direction. So rho xyz is Ey over Jx for presence of Bz. Good. Now, Righi-Leduc effect is the same thing but thermal. So that's a thermal Hall effect. What we're going to be doing is we apply a temperature gradient between T1 and T2 so that there is a heat flux, Qx, in this direction. And there's, of course, a longitudinal temperature gradient, grad xt. We apply a magnetic field, and we also develop a magnetic temperature gradient in the direction perpendicular to the magnetic field, grad yt. We do all of this leaving the circuit open, Jx equals 0. Just like here, I explained before, we do this in the absence of a heat flux. We don't have heat sinks here. We don't let heat leak out of it, but I showed in the previous lecture that that matters quite a bit. You can do it either isothermally or adiabatically, and these have different results. Well, here we're going to assume just that there is no current flowing, but we allow a Seebeck coefficient to drive a Peltier coefficient to drive heat conducted by that. The transverse effect, on the other hand, is the Righi-Leduc. Well, whereas this is a resistivity tensor element, we're going to define the Righi-Leduc effect as the ratio of grad yt over grad xt over bc. So that's not the ratio of a field or a flux, that's the ratio of two fields. So this number is a pure number as function of bz, and that's the thermal Hall. But that makes life a little bit more complicated. These are just the named effects. Now, the Nernst effect is the same as the Hall effect, except under the presence of a grad t. Nernst effect is Ey over minus grad x of t in the presence of Bz, so transverse thermal power. The Etingshausen I kept for last. So in the Etingshausen, you apply a current. And if you then develop a heat flux, that would be the Peltier effect. Of course, you don't really measure a heat flux directly. Well, sometimes we do, but sometimes we don't. Sometimes we measure temperature differences. So if you measure a temperature difference that comes from the current, that's actually not a direct measurement of the Peltier effect. You then have to correct for thermal conductivity to know what your heat flux is that creates that temperature difference. Here, the definition of the Etingshausen effect is we just take directly that temperature difference and divide it by that current. So that's another deviation from between Peltier and Etingshausen. It's the way the units work. It turns out that the literature is very, very poorly defining these things, and you always have to look at the units, because you can see that this is kelvins per amps per meter square, or kelvins per meter per amps per meter square, whereas this is a pure number. The units will tell you what exactly it is that these people have measured in their paper. I can't predict this ahead of time. I don't know, when does this show up twice? Oh, I just repeat the definitions. Now, very often in the Hall effects, or in the Nernst effects, or here, we just take the derivative vis-a-vis field at low temperature, at low field or at high field, and we call that the Hall coefficient. We call this derivative the Nernst coefficient. We call this the Etingshausen effect, but this then becomes the Etingshausen coefficient, and this becomes then the Righi-Leduc coefficient. Again, when you don't know what they're doing, look at the units. Okay, here comes a very important part of the class because most people are confused about this. Just like in resistivity, there's a difference if you measure the electrical resistivity while ensuring that the sample remains isothermal, or if you measure the electrical resistivity while ensuring that the sample has no heat escaping it. There's no heat escaping it, you have an adiabatic measurement. When the sample is isothermal, it's an isothermal measurement, and there's a fundamental difference in the quantities between isothermal and adiabatic measurements. So the isothermals is everything people calculate. It's the isothermals is what relates to the conductivity tensor and on the on-cycle relations. The adiabatic ones are mixtures, and I'll explain now what that is. So let's repeat once again. The relation between current and electric field is the resistivity if you keep everything else constant, so if you're isothermal. The relation between heat flux and temperature gradient is the thermal conductivity if you don't draw current out of the sample. The relation between the transverse and the longitudinal temperature gradient is the Righi-Leduc effect, assuming, of course, that you draw no current out of the sample anywhere. So these little conditions are important. The same here. You have the transverse, so this is going to give you the Hall effect, but the Hall effect that supposes that you have no temperature gradients, that you're isothermal. An isothermal Hall effect and an adiabatic Hall effect are not going to be the same. So I repeat here the isothermal longitudinal effects. So now let's see what the source is of this confusion. So most of the time, in the photos I showed in the previous class, you put the sample on a heat sink on one side, you glue a heater on the other side of the heat sink, and you let the sides of the sample be free. So then you put that thing in a radiation shield, and you have very thin wires. What you assure is that there's no heat flux that escapes the sides of the samples. You assure that the only heat flux in the sample is the one that you have put in deliberately with your electrical heater, and that goes down in this direction, X direction only. Okay, so if you do that, then let's assume that you try to make, let's go adiabatic Nernst effect. So you have this, you develop an electric field that's a thermal power electric field, and you develop a transverse electric field that's a Nernst electric field. But you have EY that you try to measure as function of X. You have current. Well, what did I do here? This is regular Leduc one. So I put this heater on. So I have a transverse field, and I have, of course, a longitudinal thermal field, thermal field. Now, if instead of that, I were to look at the voltage, I have a heat flux, but I also have a transverse EY due to grad T. Okay, let's start this again. Start over. Let's strictly go to a Nernst effect, and we have temperature gradient that we apply from the heater, and that's this heat flux is along this direction. So you have the longitudinal temperature gradient, grad xt. You're measuring a transverse voltage, EY. So EY has a component that's due to the grad xt, that's the isothermal Nernst. But you have a grad yt that at the same time, because of the same heat flux, arises from the Righi-Leduc effect. Now this grad yt will produce another component to the y direction due to the direct Seebeck effect along y. Repeat, grad xt produces a Nernst, but it also produces a grad yt. Grad yt produces an electric field itself that's parallel to grad yt due to the Seebeck coefficient in this direction. So at the end of the day, the total EY has two sources. It has a Nernst effect from grad xt, and it has a Seebeck effect from grad yt. And so this measurement method, you pick up EY, you don't know where it comes from. What part of it comes from grad xt, what part comes from grad yt. That's what the situation is when you try an adiabatic Nernst effect. In an isothermal Nernst effect, you make sure that you don't have this grad yt, and that the only contribution to EY is due to the grad xt itself. So when we go back to the actual on-cycle relations, back here, I have to make sure that the grad T is along X. In other words, I have to make sure that I don't have a grad YT when I do a measurement. In other words, let's do this again. Let's forget the direction. Let's put B along Z. I have LTXX, but I have along the Y direction, I have an LTYY times grad YT, and I have an LTXY as grad xt. I have the sum of the two if I leave the sides open. If I just want this, I have to make sure that there's no grad yt. Okay. So this is what the calculation gives, because the calculations come out of the LET coefficients. This is what the experiment gives if you're not careful here. Okay. So can you go from one to the other? Yes. If the difference is very small, That is to say, if grad yt is very small compared to grad xt, and then you can correct Ey in an adiabatic bound for Ey in the isothermal bound, and you essentially here correct things for what you think is going to be the Righi-Ludwig effect, the thermal Hall effect. The correction is at high field or at low field. So high field is when the product of mobility times field is larger than 1. Low field is when the product of mobility times field is smaller than 1. When we do an analysis, data analysis on our cryostats, I always quickly calculate what the corrections factors are. That's called NINA in the programs. My graduate students and postdoc will explain what NINA is. If the corrections are more than, say, 2%, you should absolutely not go this route because then the measurements are fundamentally wrong. Maybe 5%. If the difference between the isothermal and the adiabatic coefficients is large, and you only have isothermal data, adiabatic data, then there is still a way. It's called the Hörlinger relations. And I refer you to Harman and Honig's book. It's paragraph 2.15, and it's a perfect nightmare because you have to apply the Hörlinger relations. You have to make a simultaneous measurement of adiabatic Nernst, adiabatic magnetosebek, magnetothermal conductivity, and Righi-Ludwig effects. These corrections you can do with correction factors that all come from zero field values, thermal conductivity and Seebeck coefficient. So that's relatively easy to do. This is a nightmare. It's probably better to do the experiment correctly and do it isothermally instead of adiabatically, then you have a better data. Let me point out that if you measure thin films that are grown on electrically insulating substrates, you don't have a problem because the substrate will guarantee that the phases across which you measure are isothermal. If you have a sample that's a bulk sample, you have to glue it on something that's a very, very good thermal conductor so that you have isothermal lines along the y direction of your experiments. If you have a freestanding sample, well, you have a serious problem. Okay, let's move on to the next one, which is just as nightmarish, and that is the isothermal, the adiabatic and the isothermal Etingshausen effects. So, Etingshausen effect, we pass a current along Y, and we're going to pick up a temperature gradient in this direction. So it's the exact opposite of the Seebeck coefficient. Seebeck coefficient passes an electric field. You get an electric field from the passage of a temperature gradient. Here you get a temperature gradient from the passage of a current. And so it's the same story. You will have a temperature gradient that arises by the presence of the electric field that you have applied. That's great. That's what you want to have. But of course, you will have a Peltier effect. So that means you'll have a temperature gradient that accompanies your current. And that temperature gradient is along X. That temperature gradient then is subject to the Righi-Ludwig effect. So if you have a gradient along X, you will also have a gradient along Y due to the thermal Hall effect here. And that gradient along Y, of course, gets added to the gradient that comes from the Etingshausen effect. So the grad Y contains the real isothermal Etingshausen plus a Peltier effect mixed with a transverse Hall, with a thermal Hall. Same problem and same type of corrections. The proper isothermal Etingshausen is to put current and then make sure that the size of the samples remains isothermal. So that means it's isothermal in Y, not isothermal in X, of course, because you apply a gradient, or here you create a gradient in X by Peltier. Okay, now, once again, every time we do calculations, or our theoretician friends do calculations, they calculate these conductivities, the LEEs and the LETs. And then they convert them, or we convert them, to Peltier and Nernst and so on. Every time we do that, we assume isothermal. Theoreticians calculate isothermal coefficients. Experimentalists, well, we need to think about this. Don't play with isothermal Ettingshausen. It's nearly impossible, because how can you guarantee that this gradient is okay, but that one is not? So don't even try. Just use the relation between Ettingshausen and Nernst. So take your Nernst, multiply by thermal conductivity, divide by temperature, and there's your Ettingshausen. The other way around. Here's your Ettingshausen, there's your Nernst. And this is a result of the on-cycle reciprocity. It's called the Bridgman relation. I'm probably not going to go there into this class. I forgot if it has it. Okay, so let's summarize. Here's your table of effects. You have not only to apply your direction of the primary current of heat flux, you have to define what you're going to be measuring, but you also have to always define your auxiliary condition. So magnetoresistance, you apply current, you measure a voltage from which you get the resistivity. Magnetoresistance, you look at the difference between resistivity in field and at zero field, the direction of your field, and then most importantly, it's isothermal. Make sure you have no gradients. Magnetothermal resistance, here, you change the change in thermal conductivity with magnetic field. Make sure your sample has no contacts. Magnetothermoelectric effects, so this is Nernst or Seebeck's. Make sure you have no current. And then be careful, if it's isothermal, grad YT equals 0, or adiabatic, Q equals 0. So here is the situation. Yeah, you have to do this in X and Y direction, each of these. Hall effects, you have to make sure that you don't draw current between your Hall electrodes. That's this condition. You also have to make sure you have no temperature gradients on the sample. Nernst effect, you just have to be sure that you're not drawing current if you're going to do it adiabatically. And then you have an additional condition, like I said, on your gradients if you're going to do it isothermal. That is grad YT has to be 0. Correction between this and this, we talked about. Magnetothermoelectric effects, this is now the Magneto-Seebeck, same thing, open circuit. And again, grad YT has to be 0, otherwise it's going to be wrong. This doesn't affect the Seebeck coefficient at 0 field. The Nernst coefficient at 0 field is 0 anyway. But it does affect every magnetic field dependent measurement. It does also affect the resistivity even at 0 field. Okay, so now these are the adiabatic effects where you set the condition, instead of the condition grad YT is 0, set the condition QY is 0. And we went through the details of a couple of these. This is just for your information, the catalog of all the existing effects. Second thing you have to look out when you measure thermomagnetic effects is the sign convention. And this is in Putley's book, The Hall Effect and Related Phenomena. It's one of the pages there, or you can use this class as the reference. But you must be careful with the signs of all the Ettinghausen and Nernst and so on. Okay, so let's go over what we do for the Hall effect, right? Hall effect, you pass an electric current this way, and you pass a magnetic field out of the plane of the blackboard here, and you put the positive electrode on this side and the negative electrode on this side, and then you are going to have your Hall effect will be positive when your carrier is a Hall. Basically, you calculate Lorentz force on a hole that moves at the velocity this direction, and you will see that your field will deviate it so as to have your red wire become positive and your black wire becomes negative. Very, very nice. Now, we have to be a little bit more complicated when we're dealing with the Nernst effect, which is the third one here. And just do exactly what's in this view graph. Don't deviate from it, and you'll get the signs wrong. Right. Hot sides here, cold sides here. BZ is out of the plane of the field. Red wire of the voltmeter goes here. Black wire of the voltmeter goes here. Now, if you have an Ettingshausen measurement, so now you have a thermocouple that we'll call hot side and cold side. The current you pass this way. This is your hot side thermocouple. This is your cold side thermocouple. It's just what you call the couples. Of course, once you measure, it's very possible that your outside thermocouple becomes colder. Then you have a negative Ettingshausen coefficient. The same with Righi-Leduc, hot, cold, hot, cold. Okay, before I go there, I need to add that the people who first made the measurements of the spin-Seebeck effect, spin-Seebeck effect is exactly in the same configuration as a Nernst effect. They didn't know about this. And in fact, they gave the sign of their effects to the sign of the spin-orbit interaction, the spin-orbit angle, in the platinum films. It turns out that in platinum YIG, the measurement of a spin-Seebeck effect, it has a Hall convention that's exactly the opposite of the convention for the Ettingshausen effect in the thermomagnetics. We discovered this at our cost and embarrassment. Okay, now the actual measurements, we have seen this before. Measurements we do, I should take that away. They're no longer always an adiabatic mounts. Sarah Watzman's thesis will be made in isothermal mounts because we got in trouble. Okay, so you typically simply mounted sample is in isothermal mount. There she is. You have a little parallel pipette, you have the heater, you have the heat sink, you have thermocouples here and here and here, and you have voltage wires here, 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 here. Actually, we use the same wires for the thermocouple and for the voltage. Thermocouple is copper constant, and the voltage is copper to copper or copper to copper. We have mounts where we put a second thermocouple here, and we can then measure the Righi-Leduc effect, the temperature difference there. All right, this is the most accurate measurements. When you use a PPMS, they sell a commercial attachment that's called the TTO, thermal transfer, option. It's not nearly as accurate because the heaters and the connectors are much larger, and so there's always issues. This is the one that I like the best. It's simple cross-tab mounts. Okay, so this is the simplified summary of it all. You have then the voltage and the thermocouple probes here. You have the transverse voltage or thermocouple probes. And then what you have is every time a measurement of a temperature difference, delta T, which you have to convert to grad T by dividing it by the length between the contacts. The same when you do a grad YT, the same when you do an electric field, so red wire to red wire, for instance here, copper to copper, or a longitudinal electric field, copper to copper. And you need to worry about all these dimensions because the definitions are in fluxes and fields, fluxes and fields, or fluxes and gradients, which is the same. And of course your measurements are in voltages and actual heat, watts or amps. So you have to, every time, J here is, of course, the actual I divided by cross-sectional areas, and E is the actual V divided by the length. So you have a geometrical prefactor between what you measure and what you actually calculate, and this is something you need to be able to derive for yourselves for each of these coefficients. Okay, so now let me abandon the red headings, which were the general case, valid for any system, hopping, magnetic, whatever. And let's move into the classic, very simple ideal gas picture for electrons. And I can give you, again, intuitive views. So just like we had the intuitive view for the Seebeck coefficient, that you heat one thing up, cool the other side down, and your electrons are going to just condense on the cold side. So that the Seebeck coefficient, if you put your red voltmeter wire here, will give you the sign, the polarity of the carrier. The Nernst coefficient doesn't exactly do that. So the Nernst coefficient measures, on the one hand, this too. You have the diffusion of your carrier toward your colder side. That's fine. Now, if you apply a magnetic field, what matters is the amount of time that this carrier is subject to the Lorentz force. So if you have a very slow moving carrier with a slow drift velocity, so it bounces off many, many other things, it actually every time resets its velocity by the longitudinal field and is not that much affected by the magnetic field. So its deflection is weak. If, on the other hand, you have a very fast carrier, fast drift velocity, not many collisions, so the distance between the collisions is the time, sorry, the average time between the collisions is the time that the magnetic field can work on the sample, then you have more deflection. So basically, you will, I got that completely wrong. It's the other way around. This one spends more time, it has a lower mobility, this one here, and the faster one is the one that spends less time. Okay. Small diffusion, okay. Well, maybe we should not go there. In essence, yeah, this intuitive view is a little delicate. I should actually not use it. The bottom line is that the Nernst coefficient is really a measurement of the mobility of the carrier times the thermal power. And so it is something that is not sensitive to the polarity, as I will show in a minute, but is very much more sensitive to mobility and also scattering time, the energy dependence of the scattering coefficient, of the scattering relaxation time. Now, let's skip this. It's just getting myself deeper in trouble. Let's review what the polarity is. The polarity dependence is of the charge carrier. So when you have electrical resistivity, you apply voltage current that's positive on this side and negative on that side, and you have a carrier that's of a hole, that's polarity positive. So the carrier moves in the same direction as the current, and the voltage will then be here plus and that minus. If, on the other hand, the carrier is an electron, negative polarity, the carrier will move in the opposite direction of the current, but because you still have the voltage wire here and here, this is the place where it's less negative, and therefore this is the place where it's more positive. So basically you end up with the same polarity of the voltage and of the current. So that's why I say the resistivity is a number that's an even function of the polarity of the carrier. You will always have a positive resistivity. If you have a negative resistivity, that means that you have either non-diffusive transport, like in the homework problem, or it means that you have a power generator or a crack in the sample, or the sample is just completely wrong. Okay. In contrast to that, when you have a Hall effect, you have an odd function of polarity. Let me do it for you. Plus to minus, so the current flows this way, and if it's holes, they flow in the direction of the current. The Lorentz force deviates them to the bottom. Good, so this becomes more positive than that. If, on the other hand, you carry an electron, so negative polarity, the carrier moves in the opposite direction. You apply a magnetic field, so now the Lorentz force deviates the negative thing toward the bottom, and because you have the charge times the field and the velocity, now so the bottom now becomes more negative than the top when you have a negatively charged polarity and positive here, so the Hall effect is an odd function of polarity. The Hall effect can tell you what the polarity is for a carrier, then the resistivity cannot. Let's take a look at thermal power. So the thermal power, your carrier condenses on the cold side. So obviously if this is plus, you have more plus here. If this is negative, you have more minus there. That's an odd function of polarity. But let's take a look at the Nernst effect. Okay, so the majority carrier condenses on the cold side. If it's holes, they condense on the cold side. But during this general drift toward the cold side, the magnetic field deviates them with the Lorentz force toward the bottom. Now, if my majority carrier is is an electron, it also goes to the cold side. It drifts the same direction. The magnetic field applied to it gives a Lorentz force that deviates it toward the top. Notice now that the bottom is more positive than the top here, and here the top is more negative than the bottom, but that means the same thing. So the Nernst effect, just like resistivity, is an even function of polarity. And of course, thermoconductivity has the same property that's interesting. The hole goes toward the cold side. The electron also goes to the cold side, but both carry not charge in this case. We're interested only in the entropy they carry. So both carry the same amount of entropy, let's say, or the same polarity of entropy. So both are going to give the same temperature gradient. It's an even function of polarity. In contrast, the Righi-Leduc effect is an odd function of polarity. We have the same argument. Both deviate toward the cold side, but the Lorentz force, in the case of the hole, will push it down. In the case of the electron, will push it up. The charge now doesn't matter. It's the entropy that matters. So here we have more entropy on the bottom side, and here we have more entropy on the top side. So this time, we have an odd function of polarity. And so I summarize that here. Now, what's interesting is the case, for example, of wild semimetals, where the particle is kind of neither electron nor hole, but both at the same time. So if you have something that has exactly the same number of electrons as holes, both will contribute to resistivity, both will contribute to thermoconductivity, but they will annihilate each other in Seebeck measurements. They will also annihilate each other in Hall coefficients and in Righi-Leduc coefficients in thermal halls. But they will reinforce each other in Nernst effects. So when you have semi-metals, bismuth, antimony, niobium, phosphide, ytterbium, manganese, bismuthides, all the classic semi-metals, or wild semi-metals, the three measurements you want to do is resistivity, thermoconductivity, and Nernst effect. Seebeck is going to be 0, Hall is going to be 0, or very small, and contain information about the difference between two polarities, but not information that's common to both. Okay, so the last part of this topic is going to talk about the on-cycle reciprocity. Now, this is going to be complicated, of course, by the necessity to work either adiabatically or isothermally, but so let's just do this. Take a sample in which you create a sideways temperature gradient by the Etingshausen effect. So let's write the Etingshausen current here, the driving current here, and that gives you a grad YT. Etingshausen coefficient is the ratio of these two. Imagine for a minute that you connect this to a heat engine. So take a Carnot cycle or a steam engine or something. That works across this grad YT. It draws a flux JQ, and assume that the thermoconductivity is isotropic. JQ, the other isotropic thermoconductivity, gives you a grad YT, which is the thermoconductivity. This now, I just replace grad YT by Etingshausen times current, Etingshausen times current minus K. So the power delivered to the heat engine by this heat flux is going to be JQ grad T over T per cube meter. It's the density. And that is going to be just this grad YT over T. Now this has to come from the longitudinal current JC, X. And this power, therefore, has to work against an electric field that's EX. So let's say this would be the work that we would do in X. And this is the work that we get out of our machine. And so you now substitute here in EY this is the balance is EY. We substitute in EY the expression for the Nernst coefficient. So the Nernst coefficient I have to take this and I have to do EY over grad XT. Unless I put EX here. If I put EX, no. This is not right. This Y has to be an X. They don't have the editor here. So, sorry. This has to be X because the power has to come from JX and EX. And so then I have to replace EX by alpha XYZ grad YT. This is what I do here. Then I cancel the J sub X's, and then I can write that EY, this is one Nernst coefficient, is this, it's not even EY, this is EX is alpha XYZ grad YT, that's what I get here, EX is alpha XYZ grad YT. And this is what I get from the other side, minus kappa, this is the Ebbingshausen grad YT over T, from which I conclude, by eliminating grad YT, that alpha XYZ is kappa times epsilon divided by T. And that is the Bridgman relation. It relates the Nernst coefficient to the Ebbingshausen coefficient by the Onsager reciprocity. This is a quick demonstration of reciprocity before the Onsager reciprocity was demonstrated. It was done by Sommerfeld in 1931. But the reality is you get this correctly out of the Onsager relations. This was just much simpler if I had not made a mistake, if I had written an X here instead of a Y. Okay, let me remind you, we had this in the first lecture, but we have a little bit more time left to get to an hour. Let me remind you the symmetries that come from Onsager. So we saw these symmetries in the context of the thermoelectric conductances, but we didn't see them quite yet in the context of the thermal powers. Let's do it for thermal powers. So none of the Nernst or Ebbingshausen coefficients are either even or odd with the direction of the magnetic field. And this is one of the most extreme cases. This is a piece of bismuth, it's here, and they apply the temperature gradient in the y direction. This in this particular case is the O10 direction. And they then rotate the magnetic field in the, so this is in the O01 direction, and they rotate in the O01 to 100 direction. This is the field that they rotate. And what they note is the Ebbingshausen, this is the resistivity, the Seebeck coefficient. So what they note is the longitudinal voltage, magneto-Seebeck effect, as function of this angle. So you would expect the magneto-Seebeck effect to be a perfect odd function of the field, no, even function of the field, shouldn't depend. Well, it does depend. And in fact, this rotation is extremely complex. It goes like this. So the thermal power when you have B plus 180 degrees from the trickle axis is 85 microvolts per Kelvin, about right there. And on the other side, well, this actually is the same. But if you go a little bit off here, it's a completely different value. So not only is it not a circle or anything close to an ellipse as function of angle, but the plus direction and the minus direction give completely different values. So much so that sometimes they can change sign. Like for instance, between here and here, between this point, the sign has changed. Okay, so how did this happen? Well, again, you have to refer to Agos and Saunders. We talked about this in the context of the galvanomagnetic coefficients, Hall coefficients. In the context, in the context of the thermomagnetic coefficients, you have to look at which sides are even and odd. So here, these are the Magneto-Seebeck coefficients, alpha 1, 1, 1, alpha 1, 1, alpha 2, 2, alpha 3, 3. If B is B1, they have both an even and an odd component. Now, luckily, if B is B2, they have no odd component, they're purely even. So this is what you would expect, pure even symmetry. But at the same time, if you were to do alpha 2, 3 of B1, alpha 2, 3 of B1, that would have both an even and an odd component. So this would be a Nernst coefficient that would be that would not reverse with magnetic fields. Here is the symmetry. If you have B3, so in a 3 crystal, you put the magnetic field along the trickle axis, then the Seebeck alpha 1, 1 and alpha 2, 2 are going to be identical. Alpha 3, 3 not, of course, and the same in magnetic field. But the Nernst, which would be alpha 1, 2 of B3, is going to be antisymmetric. So this Nernst has no component that's even. It's a pure odd field. But if you measure alpha 1, 2 of B3, it's minus alpha 2, 1 of B3. So you don't need to actually measure these two independently. Symmetry of the crystal will tell you that if you measure one, you have the other. So what you have to do is you take your crystal, and you can have it in its enantiomorphous group. You can have it in symmetry elements. You can have it in points group, which is the one thing that I like best. There's no termites here. Your more complicated cubic structures here, or monoclinic. Monoclinic, I guess, is, I forgot. Anyway, hexagons. And then you have the notation used, which I went through, alpha XX of B. B is B1, B2, B3. XX is then 1, 1, 2, 2, or 3, 3. And we go through these elements like I explained in the introduction. And then you have to do the same. So your monoclinics have nothing, either even or odd. You can rely on no symmetry at all. And they have all the thermomagnetic components have both an even and an odd component. You can zero nothing out. You cannot symmetrize a trace between B plus and B minus. Everything's forbidden. Now, of course, if you have a nice simple cubic system, you have nice symmetries here, and you will do very well. Here, these two are the same, these two are the same. If you apply the field in a different direction, this is a longitudinal Magneto-Seebeck here. That, of course, can be any number of things. Refer to this paper every time you have a symmetry problem, just like I mentioned you should do in the galvanomagnetic coefficients. The symmetry of the thermomagnetic coefficients is much lower than the galvanomagnetic coefficients. This is going to be higher. And that's it. Thank you.